you very much. So spontaneous spatial coupling is a hybrid technique of motion correlation and cursor-based interaction. It enables the appropriation of any body part or movement of a tangible object to be used as a pointing device on an ad hoc basis. The technique can automatically account for the user's range of motion, and the pointing phase only needs to persist for as long as the user requires. So a step-by-step breakdown. So in the first instance, controls are displayed to the user in the form of moving targets. So here we have 6 targets, and 3 rotate clockwise, 3 rotate anti-clockwise, all with different phases, so each movement is unique. And in order to interact with the display, the user needs to mimic the motion, and they can mimic the motion with any body part or tangible object. The system looks at its inputs, which is the user's movement, and the outputs, which is the moving targets. And if there's a correlation between the inputs and the outputs, a pointing phase is generated. In this case, the user selects the channel using the horizontal movement. But it's also important that they can decouple from the control. So in this case, we use the vertical movement to select the channel. And the system reverts back to the motion matching phase. So we leverage 2 different techniques, each with their own advantages. So motion matching is highly discoverable and intuitive. It is great for simple binary tasks such as playing or pausing, muting the volume, and it's suitable for multiple users and can be performed with any body part or object. In contrast, cursor-based interaction is a familiar paradigm that we use in our everyday lives and is good for continuous interactions and object manipulations. It too can be used by multiple users with any body part or object. But when we combine these approaches, we can leverage further advantages. So the pointing is only activated upon the selection of a control and only needs to persist for the duration of an interaction. So this effectively shifts the Midas touch problem we have with cursor-based interaction to the motion matching phase, where we can control and design specific motions to alleviate this problem. We can use different body parts or objects to instantiate pointers, and the scale and range of the user motion in the motion matching phase carries over to the cursor-based interaction. So problems like gorilla arm are alleviated because the user can switch input modalities, and ill mappings tend to be avoided because we can define the range of the user's motion. We can also tailor the pointing to the context of the interaction, so depending on what type of modality the user uses, and also depending on what task they are trying to complete. So we introduced MatchPoint, which is a webcam implementation of the technique, which accepts any type of motion as input, and is built upon the trace match system, which was introduced last year at UbiComp. And this is how it works. So in the first stage, we use feature detection and optical flow to track unique features in the scene, which we match against the moving targets. So here we have yellow and green features. Green features are points which exhibit enough motion to be considered a candidate for the matching process. We then use a Pearson correlation and fit a circle using the ransack method to detect whether any of the features have matched the moving targets. In this case, we have 2 features. We can use the ideal user's motion derived from the ransack process to calculate the CD gain. So for example, head movements will result in much smaller motions than hand movements, but we have a problem. In the next stage, we want the cursor-based interaction, and we need to track the object or body part which match the motion. So we retrospectively look at the dense optical flow to see which pixels match the motion of the target. This allows us to initialize the pointing in the tracking task, and then we use a modified version of a median flow tracker to track the object or body part for the cursor interaction. So there's a number of techniques. The conventional pointing paradigm of having a single pointer control all the elements on the interface can be leveraged by decoupling, allowing the user to decouple from the pointer as and when they require, and to change input modalities. However, it doesn't really leverage the advantages of the technique. Having multiple pointers with multiple functionality means different pointers can provide different functionality. And the CD gain can be mapped to controls rather than interfaces. So in a TV example, you could have a TV guide using a two-dimensional pointer. You could have a channel selection using a horizontal slider or a vertical slider for the volume. We can do similar things with a video player, such as controlling the playback, selecting the progress of the video, and once again using the volume. So here's an example of using the inbuilt camera of a surface to rewind a recipe using the hand mixer. The user doesn't have to stop what they're doing, put the object down. They can interact with the system and carry on their task. The problem with the previous approaches is you can't have multiple users controlling the volume or selecting a channel. It gets a bit messy. But you can have multiple users interacting with the same control, which, for example, you could use to contextualize discussions. So in this example, we have two users who are contextualizing a discussion on a house plan from a distance, both acquiring the same control to dictate the discussion. We can also have parallel pointers, so a single user can acquire multiple pointers, and this can be to complete tasks more quickly, to enable more complex interactions, to manipulate one control based on the state of another. And we can categorize into three categories. So the first is unrelated, so the control of one pointer does not affect the other. So for example, in a smart home system, one might change the heating while changing the volume of the radio. These are unrelated, but the user could do them at the same time. You could have loosely coupled, so the pointers affect the same object, but could be used individually. So in this example, we've got two pointers. One controls the panning of an object, and one controls the zoom. And a user can use different input modalities to control the pointers. So the head controls the zoom, and the hand controls the panning. We can also have tightly coupled pointers, in which the interaction results from the relationship between two pointers. So in the same object manipulation example, we can have bimanual input, where acquisition of two pointers allows the zooming, panning, and rotating of an object. So far, we've looked at temporary bindings, but tangible objects present a unique use case, as they can act as an intermediary between the user and a control. Objects have interesting properties, such as being able to be left stationary for prolonged periods, and they can afford specific manipulations depending on the type of object. So in this example, we have a radio player, where objects are assigned to different controls, such as changing the song, the playback, and the volume. Each object is in turn coupled to one of the controls, and this time a persistent binding is created, so that manipulation of the object results in manipulation of the interface itself. So this opens up a new design space. We've provided initial framing with a few examples, but this supports a wide range of applications, as we can appropriate anything the user can move. So we can have combination of body parts, objects, more persistent object bindings. The users can manipulate multiple controls at once, and you can have one or multiple users doing this. And this opens up for the exploration of mappings for specific contexts rather than general purpose mappings. Input can be uniquely tailored to the context, depending on the method of input the user decides, the calibration of the CD gain, and the task in which they aim to perform. And this in turn is enabled by the motion matching, which is at the core of the concept. And in one fell swoop, the motion matching phase acquires the pointer on an ad hoc basis, selects the function that the user wishes to control, dictates the body part or object to be used in the interaction, and defines the user's range of motion. MatchPoint requires a simple, unmodified web camera. It's low cost and highly deployable, and the choice of input is free. The user can choose the choice of input. But other sensors could be used with the technique. So we could extend into 3 dimensions using depth sensors, or use inertial measurement units in mobile or wearable devices or head-mounted displays. An important point is that MatchPoint makes no assumptions of the users or the objects. So there's no training or calibration. It's posture agnostic. The user doesn't have to be in the scene as long as the motion they generate is witnessed by the camera. And this has big implications as an accessibility device because most gesture techniques assume the user has hands. In this technique, as long as the user can generate some form of motion, they can use the system. But it also opens up the question of whether one should design for a specific input modality. It's been shown in the past that the hands outperform the head for pointing. And if we design with all input modalities in mind, we'd have to design to the lowest common denominator. However, in future work, if we added post hoc object recognition, interfaces could be presented depending on which input modality the user uses. We use circular motion, but any shape can be used for the motion matching. It just depends how distinctive the motion is and how easy the users can replicate it. The output device also doesn't have to be a display, as long as it can display motion that the user can synchronize with. The feedback also doesn't have to be visual. For example, with a radio, movement can be fed back to the user through audio channels. So, spontaneous spatial coupling is a dynamic technique which appropriates any body part or object as a pointing device, leveraging the benefits of motion matching and cursor-based interaction, and it's a flexible and spontaneous touchless input over a distance. Input can now be uniquely tailored to the context, depending on the way the user manipulates the interface. And MatchPoint is highly deployable and flexible. And we believe this opens a new design space for exploration. Thank you.
Sorry. So how much computing power do you need? Does it run on a really small device? So that the matching, or does it depend on the complexity of the scene?
It depends on the complexity of the scene. So at the moment we run it on desktop computers or surfaces, but we're currently developing mobile applications. The feature detection is the limiting factor in the CPU, but we could also optimize the system using the GPU. So.
Hi, it's Andy Wilson from Microsoft. So this is nice work. I really like it. was curious if you had any idea how to answer the question of if you have lots of motion in the scene, how reliable is this system? Now there's lots of different aspects of that question that are sort of frustratingly vague, and I was wondering if you had an idea about how to even approach evaluating that reliability.
So the system is built upon trace match, which was introduced last year at UbiComp, and we've just published a user study at this year's UbiComp. And in that we looked at trying to avoid false positives. However, we only did it with a limited number of users with a limited number of tasks. So for example, we didn't use a crowded scene. But we designed the system according to the trade-off between making it open enough so that users can accurately match the motion, whilst constrained enough so that we avoid the false positives. In terms of a crowded scene, we'd need to look into that.
Okay, thank you.
Thank you.
Perhaps I have to follow up, and somebody else can also think of a question. So the complexity for the user. So I think I really get sort of the second part once I have locked to the motion. That's really neat. Do you have any experience on the first part? Sort of how easy is it for people to really get the concept of that they have to mimic with their interaction a movement on the screen?
So once again, referring back to the trace match work, the users seem to acquire the capability very quickly. Depending on the input modality, really depends on how well they can match the motion. So everybody using hands and objects performed brilliantly. Head motions were a different story. So we looked at two different speeds, and for fast head movements, a lot of users performed very badly. In terms of how spontaneously people can pick this up, there's a work on called PathSync, which used a Kinect for motion matching, and they deployed this as a public display, and which users would just walk up and interact, and they had no problems.